Hello, everybody. Just after this break, so hopefully you had time for a quick coffee. I always love to just look at the coffee machines and see how many pi tags are on those coffee machines. Unfortunately, we have a lot of handheld device here, so I think the manual logger needs a little bit of additional help here. So today I will talk about data cleansing, anomaly detection, outlier analysis based on OCS, OSIsoft Cloud Services. And hopefully, if you've suffered through data cleaning in the past, how many of you could have suffered from data cleaning in the past? Show of hands, a few? Okay. Then hopefully the content of this presentation will be interesting. Who we are. Unfortunately, my friend Fouad couldn't make it, so I will be presenting his portion of the slides from vExchange, great co-location provider and deep user of the Pi system. And myself, Rémi Duquette, Vice President at Maya, HTT. I think you've seen us on the main keynote speaker earlier yesterday, and hopefully today's content will be interesting. A little bit of background. I always like to set the stage with, what's the value of information? If we want to leverage the raw data, clean it properly in a systematic and reliable fashion, why do you spend that time to do that, right? And it goes back to what's the business case and what's the value of your information. So going from raw data to information to eventually wisdom and AI and other stuff that you can build on top, there's a reason. And I've always searched for the value, what's the dollar figure for information? So just dawned on me at some point, if you look at Google, they're now at $136 billion. And what I've done is, I'm a scientist. I like to, I'm an engineer, mechanical engineer background. I looked at the number of dollars divided by the number of search per year. That's about 7 cents per search on average. So that's essentially what this information is worth when we do a little search, at least from a Google perspective. In any case, this is just one data value point. Your data is valued by the use that you make of it. But it was just kind of interesting to find a clear case that we can all understand how we get to the value of information, which was kind of interesting. Anyway, with that stage, today, introduce a little bit of who Maya and vExchange are, very briefly. Then I'll dive into the core of the subject, which is really, in this case, vExchange data center business challenges and how outlier analysis, data cleansing, and anomaly detection was useful for them. The CRAC unit, computer room air conditioning system. I see a lot of acronyms at this conference. I don't know about you, but we should make a little list of all the acronyms in the different markets and industries. It's kind of interesting. Probably come up with a phone book worth of acronyms. Then a little bit of introduction on the outlier analysis, the algorithms, what's behind it, low dimension versus high dimension, telemetry, and all of this good stuff. And then some other use cases on how you can better leverage OCS and get the most value out of OCS as a cloud service platform. So, Maya, we've been with OSIsoft since 2012. We have an OEM agreement for Data Center Clarity LC, so if you're in the data center space, chances are if you have OSIsoft Pi under the hood, you're probably one of our joint customers as well. Since this year, since OCS was released, we're now onboarded some anomaly detection app and the smart building app that you saw yesterday. In terms of our background, so that's a marketing slide, but essentially we're a very technically oriented company, about 200 people, mostly based in Montreal with offices in the UK for Europe to service the European market. I come here in Europe pretty much every month or every second month, so if I get the chance, I'll visit a beautiful country where you're from. vExchange, so the core of the subject here, leading provider of co-location. So they're an owner of 14 data centers across the US, pretty large data centers, talking in the upwards of 10 megawatts of a data center space. So of course, for them, the uptime and the reliability and resilience of their infrastructure to support the IT equipment that are running in their data centers as tenants is really the key business driver. So if you look at their 3 pillars from a business perspective, resiliency is probably the top in terms of their end users, which probably some of you are hosted in some data centers. You want uptime, and you want all the services to satisfy the service level agreements that you've signed with that co-location owner. And for them, it's to ensure that they keep that contract and those promises satisfied. On the secondary side, for them, for their own business, they need to grow, they need to forecast, and for that, they have all sorts of tools to see how to grow their business. Now, today I'll focus on a few operational challenges. The first main one will be around computer room air conditioning systems. In their case, they have well over 300 crack units, as they call them. And no, we're not talking about drugs. We're talking about computer room air conditioning units. Across the 14 sites, they were very fortunate. About 80% of those crack units were from the same vendor, different models, but the same vendor. So they were having quite a lot of data that we could leverage for outlier analysis, data cleansing, and anomaly detection on the back end. So all of that for anomaly detection was to meet here. That's their SLA to their tenants. The 4 nines are real. That is their promise to their tenants, that's the uptime that you're going to get if you go into their data center. So to keep that up, they've built, for the last 4 years, essentially a platform based on Pi, and the software layer on top, which is their digital twin, so to speak. I prefer, by the way, to use digital clone. A twin kind of implies that there's a little bit of differences. Clone is a better way of seeing, it's the exact same copy, you're just overlaying different data on top of it. But anyway, minor, kind of scientist point or engineering point. They have their digital twin, digital clone, where they overlay all the data to have context and see where things are, where the anomalies occur, not just the raw data, right? Not just the telemetry, but also where the alarms and where the anomalies occur within their context. And if there's something that starts a problem, they can see it kind of trickling in 3D as to where it started and where it's ending. So often you see the endpoint, you get the alarm on a bunch of racks, but really it's something upstream in the UPS side or the crack units in the area that failed before you get to the real problem on the rack level. So in terms of the specific use case that we've leveraged within OCS, so if you look at crack units, they had 300 of them, about 24 streams attributes each. A stream is, you can say, equivalent to a Pi tag in the OCS context, although you can have multiple attributes under a stream, but we'll pass those details. Let's just say one stream is one Pi tag for now. And here, from a dimensional size of the problem, you can imagine if you have 24 attributes times 300 crack units, you're already 7,200 columns, if you think of it as a high-dimensional case, and you have as many timestamps as samples as you can get from your telemetry. So that's about, in this case, if you look at just the last 90 days on a minute cases where you bring your data views from OCS, that's about 129,000 lines. That's not that bad. Of course, if you go on a second level or lower or longer period, then you get big, let's say, complex mathematical problems and different algorithms to solve them. On the output of this use case, from an outlier perspective, we found about 20 outliers per crack unit over the 90-day period that we looked at in OCS. So that's about 6,000 outliers. Now, I'll get to describe what an outlier means. Some of them are just data errors. In their case, about 14, on average, 14 out of 20 were just data errors. And that's going to be the nice side benefit of these high-dimensional anomaly detection algorithms, is you're going to actually find out that you can clean your data in a reliable way because they all appear as the same outlier context. So we'll get to that in a few slides. 6 of them, though, were true outliers that may or may not be an anomaly. And I describe 2 terms here: outliers, which is something that's weird, right? But it doesn't mean that it's bad. It can actually be weird and really good. It's just an operational efficiency status that you've never seen because of all sorts of different, combinations of attributes that lead to that, high efficiency. So sometimes an outlier can actually be a good thing. You want to repeat it. So we'll get to those different classes in a few seconds. But in any case, in their situation, so that turns out to be about 1.4% of all their timestamps had some sort of an outlier context to it, something that's strange happening in the telemetry that they were collecting. So we'll get to those specific things. Crack units. How many of you are kind of running similar equipment as computer room air conditioning units? Any in here know a little bit about cooling systems? No? Okay. So I'll describe a little bit more here what these units are. So the crack units are on the right-hand side here. They take the warm air coming out of all those servers. They essentially feed it here. All the coils and the airflow goes through the crack units. Heat is exchanged at that level. The cold air is fed back in an underfloor. And then in front of each of the cabinet in a data center, you have little perforated holes in your tiles, and that cold air seeps in front of those cabinets, and then they're sucked back from the servers, right? And that's just a circle of life for that air inside the data center. If you look at the anomalies, so whenever we go into a discussion about anomalies, I always stop and say, let's list, assume that you can find those anomalies, right? What do you think are the anomalies? And more important, what are the actions that you would take to resolve these anomalies if they appear in your data, right? You live these things day in, day out, so you know what problems, typical problems you encounter in real life. So from these stakeholders that are, managing those crack units, you can easily list, and in this case here, that was the list that we came up with them, lack of blower motors lubrication, dirty blower motor fan, so very practical things, right? So from these, you can then find what is the action. If we do find this in the data and we can reliably repeat and find those as they appear or predict for them, what would be the action that you would take? So we listed the maintenance programs that were attached to these anomalies. Some of them are a little bit more complex because they can be similar in terms of the data pattern. If you look at thermal anomalies from inefficiency and airflow pattern, meaning that you have blockages under the floor, lo and behold, in a data center, you have lots of wires. Well, guess what? A lot of the wires go in the underfloor. They create blockages, they move the air in different areas, and there's some areas on the underfloor that actually get shortchanged. and they don't get much cold air seeping back in. So now you're getting into a vicious circle of pressure differential that sucks back hot air from the back of the rack into the front of the rack. You get into all sorts of bad situations. But if you compare this to anomalies where you have mixed air temperatures, so in this case here, we see that the hot air is going back into the crack unit. In most cases, in most data centers, that's not quite what happens. There is some level of hot air that will be mixed back with cold air before it goes back into the crack units. So you can interpret that as, well, I have inefficiencies in the flow pattern, or in this here. So depending on what you're tracking and where you're tracking it, you may be more or less accurate in that judgment call between those two problems. We'll get to that in how we differentiate between those. And when we see, and this is why it's important to list those anomalies up front, once you have those anomalies listed, you know which ones will have potential clash in terms of the detection, right? What information can you get from your telemetry that will yield a proper judgment between these two patterns? If you don't have the data here, well, you're never going to be able to differentiate between these two, right? From a telemetry standpoint, if you don't have the data points to differentiate it, well, you can't do it. So in those cases, you can instrument, you can add a few sensors, and then you're in business. So if we look at one of the big gain from doing outlier analysis and anomaly detection is actually data cleansing. And I never realized how crucial and important it was until we started on this journey, especially with OCS as the platform to move the data to. You've probably seen a bunch of these. I've isolated the top 5 in data problems, data errors that might occur in some of your systems. If you look at isolating some of those, well, from an outlier's perspective, they will all appear in different ways. And here, you can easily label these, because they're all on the line of 0, or in this case, -1, because they were labeled properly. So all of these were automatically labeled as data errors. You have a bunch of outliers on this screen here, but the ones that are easily identifiable as errors are the things that makes no sense. And so when you look at the outliers just together, without the data, right, just the outliers, you will always be easily finding those and being able to, let's say, put those errors on the side. So whether they come from bad data, invalid data, calculation failed, that happens. You divided by 0 because you didn't know that it would ever be 0 in your equation in pi. Cannot convert some of the units transitions, communication failures. Some of those happen in the early stages of deploying a Pi system, but often they stay there, unchecked or unexpectedly in the system. So we can then easily find them with this. No data happens from time to time for different reasons, and that can also be left here from a categorical perspective as something that happens infrequently, so it will be seen. Of course, if in one of your Pi tag it's always no data, well, it's not an anomaly, it's always no data. So someone should have seen this, but anyway. There are some few, gotchas from time to time. But again, in a high-dimensional anomaly detection, if one of the columns is all no data, the entire column will be split aside as an anomaly. So that becomes an attribute that's in its entirety is an anomaly. So that's an easy way to find that there are tags that were completely not working during your system. So if we go back to the crack units, if you look at specific things like motor overheating, power and amp spike, and power spikes, here in the interface from the OCS data that was collected from these 300 crack units, we essentially isolated and clustered these different scenarios. and essentially gave tools for, and my colleague Warren in a few minutes will show you a little demo of this here, how you can quickly investigate what these things are, right? They're outliers. They've been pinpointed as outliers. But what are they really? Are they an anomaly or are they not an anomaly? So this is where the end user will look at the data and will be able to attach labels to it, but very quickly put thousands of those labels to that data set. Because first it's been clustered by the algorithm automatically. So you have a first step that's done for you, and you have a long list of clusters that are appearing in the interface. And then you can label them and then feed that for your machine learning and other training for anomaly detection on the second step, on the back end. Another use case in data center is the fact that you have, from a tenant perspective, you're running these IT devices, and what you have often is what we call ghost servers. Servers that are running at about 40 to 60% of their maximum power, but they're not doing any useful work. They're just spinning the CPU for nothing. And that happens in about 10% of the cases. The challenge is trying to find them. If you have a small-ish data center, at least from a co-location perspective, of, let's say, one room with 500 racks, well, you're going to have maybe 800 of those. But where are they in those 400 racks? Well, good luck, needle in the haystack kind of scenario. So this is where anomaly detection will easily pinpoint those ghost servers and say, here's your list of ghost servers. Reason it can pinpoint it, the CPU thread is 0%, and the max power is pretty level and flat at 40%. So it's a very easy anomaly to detect in a data center from that perspective, but it has a big value because then you can repurpose those 800 servers or whatever number of servers that you have to other tasks. Right? So from an IT deployment and forecasting and usage perspective, you can maximize the use of that through outlier analysis. So when we talk about outlier analysis, a lot of people refer to this problem. How you can track in real time and look at seasonal impact and from one variable getting a drift in the sensor, so getting out of range slowly but surely, or spikes or shorts or components in a one-dimensional view of a time series. Now, I'm not going to say this is super easy, but it is fairly common, and there are tons of tools that can do that. If you have a PI system and you've seen probably in the trade show floor the analytics boot of OSIsoft, you can see you can use Python and essentially feed that and feed it to a seasonal decomposition model. And it's fairly straightforward and easy to discover those. The problem gets really complex when you look at multiple variables. In most cases, in real-life cases, especially in data centers, and I'm pretty sure in most of your cases, any units or assets that you're managing will have a bunch of attributes that are telemetry from the operation of that asset. But you also have external attributes, temperature, humidity, other things that are interfering with it. Could be maintenance, whether it's planned or unplanned, that comes in the way. Well, those multiple variables and multiple time series need to be taken care of in a very different way than this case. And when we look at multiple variables, there's really two sets of algorithms again, some that are very simple for what we call low dimension, and it's about less than 5 variables. You typically can use those algorithms that are fairly simple. When you look at a factory that has 15,000 PI tags, and yes, that's a real case of a factory, where you manufacture a bunch of things and then you collect at each discrete manufacturing stages a bunch of telemetry and manual inputs, you get easily to those kinds of levels. A pump that has 32 pi tags, a crack unit that has 22 of them. In all those cases, this is what we call high dimension. High dimension typically is more than 10. Okay, so if you have more than 10 variables, don't try standard techniques. Okay, they will fail. I guarantee you, don't even try. I mean, you can try if you want, waste time, but it's futile. So even at 32 pi tags, so 32 columns and 1 million rows of samples that you have of telemetry, you need different algorithms for that. So now, when we look at OCS, and that's why it's such a great platform to move the data in OCS that you can then apply various applications on top. And I'm sure Laurent from OSIsoft can give you a lot more details on how to set this up. But the essentially Pi to OCS agent is what you typically set up to move the data. And you can move it from multiple Pi systems into one OCS namespace and build very interesting and useful data views inside OCS that the apps can then consume. In terms of the app, that's the outlier detection app that we've put together here. What it does is essentially goes through these different buckets of outliers. So the first one are the data errors, right? These will show up as outliers, but they're, again, easily identifiable because they have specific patterns in them that are different than the other 3 sets of outliers. Another set of outliers, there are things like, well, guess what? There was a tsunami and everything will appear as outlier that day, right? So clearly, it's not controllable. It's not something that is repeatable. It's not something you can do anything about. Well, in those cases, you want to be able to say, for that time frame, just forget it, right? We don't want to keep that. Now, the other 2 are the ones that are the most important ones. Advantageous anomalies, so event conditions you actually want to repeat. And yes, those exist in your data set. I'm convinced of that. And then there's the disadvantageous anomalies, where those are the things that you want to avoid, prevent, forecast, and make sure you can not repeat those events in the future. So when you look at categorizing those things, most people will go through these different steps of, SME interaction, so subject matter expert that looks at the anomalies and the labels that they've had in the past or that they want to forecast. They want to use the data access and look at the data engineering for the problem. They then clean, right? This is where you suffer, if you've ever done it. That's where you spend a lot of time, typically about 30% of the project time. Then you do your algorithms, and then the SME validates it, and you put in the operations. That's a typical way of doing data science or machine learning or any other projects today. Now, what we have helped VXchange with is that 50% of time that is spent really organizing the data, cleaning the data. That's the most important step that the outlier algorithm will help you with. So, and the second thing is, once you want to get it, make that thing operational in the remaining fashion, well, if you take that data, let's say those 300 crack units, right? Take all those columns and those timestamps, you take it offline, you give it to a data scientist. What's going to happen? Data scientists will clean the data. It will normalize the data. We'll do all sorts of manipulation to feed it and train the algorithm, right? And then that algorithm will be trained on pristine, beautiful data. Well, guess what? Here in operations, you have raw data. You don't have the 2,500 steps that the data analyst has taken to train the model. So often people will get humongous failures in their machine learning because there's a big disconnect between what's been done here and what happens here. OCS and the Maya app will help you here, of course, but most importantly here, because then it's repeatable. All those data errors that you've labeled as data errors will be taken into account in the way that you want. Some will be ignored, some may be replaced, some may be mapped, but it will be systematic. So the raw data here going into the training versus the raw data that goes into operation is exactly the same because it's been cleaned the same way in a systematic fashion, in a reliable fashion. So that's really the setup that we have with vExchange, and we push the data through PyOCS agent into OCS. We have the microservices in the app that helps the user essentially select either the data views or select the assets and the attributes that they want to take into account, and then move that into the outlier buckets. What's next for them is to grow to more number of sites and more data views. Now that they've seen it in the context of the crack units, now they're going to go and maybe UPSs and other components that they want to attach. On this side here, they want to extend to the automation, the outliers, to be detected and being fed back into their digital twin model. So that's the next step there. So very briefly, I'll get Warren to come in and do a 3-minute demo.
Okay. And then
if you click there
again, it should.
It starts, yeah.
Okay, perfect. So yeah, so this is the app that we put together to show the results of the algorithms that Remy was talking about before. So you have the set of clusters of outliers that we found. You can kind of flip through the various clusters. When you go to look at a particular cluster, you can see information about the cluster in terms of how many outliers are found. You see kind of an overview of all the clusters. One of the things that the algorithm does is, okay, I was hoping I could pause this. Let's see if did that work? Okay, it did. So you see in the upper corner here, you see the breakdown of the various influencing attributes. So when we go to look at outliers, we identify the things that are most influential in terms of making something an outlier. So we start out by showing you the typical point of the cluster, and then you can identify what the outliers are for it here. And then at the bottom of the screen, you can see the more information about those influential outliers, showing the time. The green line shows the time that where we detected the outlier, and then you can see the curve about 20 minutes before and after, showing how that outlier was behaving, or that attribute was behaving just before and just after the outlier event. And the idea here is to be able to identify what the actual cause of the outlier is. As Remy said, it could be an expected event, it could be something that's good, it could be something that's bad. But a subject matter expert can take a look at this. We show the kind of the distribution of the attributes over the entire data set and the distribution across the clusters. So you can see whether it's in this case, you can see that the amperage and the kilowatt hours are much, much higher than the global set. And so that would give a subject matter expert information about what's really going on. And then you can go up and you can actually start labeling the entries. You can add whatever labels you like. You can apply them one by one if you want to go through and look at them individually. But you can also, using the scatter plot of all the various outliers in the cluster, you can go in here and click on individual ones and then see how they behave. Down to the bottom here, you're seeing the comparison between the current outlier you're looking at and the typical points. You can identify whether they're actually the same issue or not. If you identify that a bunch of them are the same issue, you can basically go in and apply that tag to a bunch of them at once by just drawing a circle around the full set. And it makes it very easy to kind of tag a large number of them at the same time. You can also identify, if you have, like here, it looks like there may be two different clusters. you can actually go in and you can look at the data from the other cluster as well, and you might identify that this may be a slightly different issue. And so you can go in and add a different tag to those issues. And so the goal is to make it very, very easy to tag large numbers of outliers that look to be the same in a very simple, quick operation. So you can see here we're adding the another tag to these. So it makes it very easy for a subject matter expert to go through and identify kind of the root cause of these various outliers and then tag them. And then that can lead to, as Remy was saying, various other kinds of algorithms, data cleansing, hooking that into various machine learning techniques as needed based on the kind of information you find.
Perfect. Thank you, Warren. So another use case that we've started on, and you've seen a little bit yesterday on the smart building application, and I thought I would show it because it's a similar setup. In this case, the OSIsoft headquarters has about almost 20,000 streams that were moved to the OSIsoft Cloud Service, OCS platform. And from there, we're able to ingest this and get a list of outliers. And then in the end, we can also move it into the digital twin in 3D. And if you're interested after, I can show you on the iPad how that works. And you can zoom in, pan, remove floors, do whatever. So if you're interested in seeing that, just come see me after the talk. So to give a little bit time to questions, let me go through here the second to final slide. So conclusions. When you look at the challenges that vExchange faced, first they wanted to create clean input for doing machine learning, AI type work on top of their crack unit data. Now that task, when they started on their own manually, was taking them a month of Sundays, and it was slowing down those analysis that were quite needed. And so when they approached us, we quickly moved them to ensuring that that was taken care of. Now the other aspect was once they had trained model, as anybody else, they were feeding raw data that was not as clean as the data that the algorithm was trained with. Even basic machine learning or even statistical-based model would have failed in those cases, right? So it's just best practice that they needed to apply here to train those models. And then the labeling task can be daunting, right? If you have thousands of those outliers that come out, how do you reliably label them so that you can then feed it to a training the model? Training the model in the end, in practical purposes, machine learning, we talk a lot about AI, deep learning. It's not rocket science, and believe me, I'm a rocket scientist, by the way, by training. It is not rocket science once you get clean data and label data, right? The difficult part is if you don't have clean data and you don't have labels, well, then that's what's taking a huge amount of time to get to results. But once you do have that, and that's what we're enabling here, is to take a whole bunch of Tetris blocks that you don't know what color they're in because you don't know what anomalies they are. You know they're outliers because clearly they're falling on you and you have to react to them, right? So what we're helping is to color code them into the right colors, and whether they're sideways or coming different ways, we color code them, cluster them, and then help you stay alive and remove those from the Tetris game. I thought it was a good analogy, but anyway. Benefits, automatic and reliable way of cleaning your data. And in all systems, and we come from that world of automation and mechanical engineering and chemical engineering, you always have things in operations that happen. And sometimes you can control it, sometimes you can't. But the one thing you can control is if it does happen in a regular fashion, you can cleanse it on an algorithm level. And that's kind of the next step. If it can be clean up front, great. In many cases, you're just, keeping your fire hose and cleaning all the fires that you need to attend to, so you may not have time to go back and clean the data and make sure that it doesn't happen again. So these will typically happen, but here at least you have an automated way of doing it. Automatic clustering was one of the benefits. So when you have thousands of those things that are the same thing, well, instead of manually labeling each of them, we found nice ways with scatter plots to just like lasso the whole thing and get a label to it, and then it goes into the database that you can then train on. So that kind of ways of transferring OCS data to outlier to anomalies that are labeled that you can then train beautiful algorithms on them. And that's really the 10 times faster labeling of large amount of data. That's probably an understated value here, but we're conservative engineers, and it's a round number, so it's good. Now, if you have an interest in trying the app on your use case, we're still in the process of getting early adopters, people that will influence the development of and the results of the app on top of OCS. OCS was released roughly in June, I think Laurent was. So it's still, we're early on top of it, but we're definitely interested in engaging with some of you. So vExchange and others have joined us to make this a great tool for all of you. If you do want to participate, come and see me or Warren. We're here for the week, so anytime you want to see us, and we'll sometimes, let's say, roam around the OCS booth within the OSIsoft booth down there in the trade show floor. So on that, we have time for a few questions, and to essentially enable some questions, I have some of my family maple candies. I'm from Canada, and we tap 10,000 trees. So if you do ask a question, I will give you a little lollipop for your kid. And they're great, natural sugars, Any question? Tempted? Oh, one down there.
Thank you for the presentation. My name is Ewan Phillips. I'm in a transmission business in Scotland. One of the questions I've got is, do you have to use the cloud service in order to use your application, or could you run it in a server? Or?
So at the moment, the engine could be run offline on premise if there was any issue with moving the data to the OCS cloud. Of course, we hope that with the advantages that you would benefit from on OCS, you'd consider it. But if not, we do have a way on premise to run it. Yeah. And you deserve a little lollipop for that. Oh, you gave it? Okay, good. Any other questions? Nice maple candies awaiting. Good.
Okay. Round of applause for Remy, please. And
thank you.